This video is part of the MCAT chemistry video course. Subscribe if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to start going over equilibrium, and we will start with Keq and then the reaction quotient. Equilibrium refers to when the rate of the forward reaction, so the reactants turning into products, is equal to the rate of the reverse reaction, so the products turning back into reactants. So whenever those are equal, we are in equilibrium. This does not mean that the amount of products and reactants are equal. So even if we had, let's say, 100 of our products, so 100 of each of our products, and then 10 of each of our reactants, if those reaction rates, the forward rate and the reverse rate, if those two are equal, then that reaction would be in equilibrium, even though the amounts of products and reactants are not the same. And you want to make sure you understand that these reactions are still happening. So even at equilibrium, we do have some reactants turning into products, and we have products turning back into reactants. So there is something going on. But because those two things are happening at the exact same rate, our concentrations remain constant. So we're not going to be able to observe any change of products and reactants, even though there is something happening. The equilibrium constant is a value that tells us whenever equilibrium is reached for a particular reaction. And it's going to be very dependent on that reaction. And Keq is what we use to represent the equilibrium constant. Keq equals the concentration of the products on top. So we have the concentration of C and D, and then we raise C and D to the power of the coefficient. So the lowercase c would be whatever the coefficient is in the balanced equation, and we raise the concentration of C to that power. We do the exact same thing for product D, and then we put that all over A raised to its coefficient and B raised to its coefficient. So whenever you hear products over reactants, this is pretty much what it's talking about most of the time. And notice how, because there are four variables, we have A, B, C, and D, there are a lot of combinations of different numbers that could get you the Keq. So you don't necessarily always have the exact same concentrations of your reactants and products to get you to the Keq, because there's many ways that they could combine to give you the Keq. And it just depends on whatever particular problem that you're working with that those concentrations end up being. Next, we have the reaction quotient. The reaction quotient is super similar to Keq, and if you look at the bottom here, we have the equation for the reaction quotient. Q is the letter used to represent it, and notice how it equals the exact same thing that Keq does. It is products over reactants, and everything is raised to the power of the coefficient. The difference between Keq and Q is that Keq told us the products over reactants whenever we're at equilibrium, so the rates of the forward and reverse reaction were equal. Q tells us the concentrations of products over reactants anytime that we take a measurement. So if we just started a reaction and the forward rate and the reverse rate are not equal because the reaction hasn't had time yet to reach equilibrium, and then we decide to take a measurement of products and reactants, the value that we would then get if we plug those numbers into this equation, that would be Q, because we're not at equilibrium, so it's not Keq. So instead, we call that value Q, or the reaction quotient. We can compare Q and Keq to give us some really valuable information about what direction the reaction is going to go. There are three possibilities. The first one would be that Q is less than Keq. So let's say that for this reaction up there, we know what Keq is because it's a given value. And then we take some measurements of the products and reactants, and then we calculate Q, and it comes out to be less than Keq. What that tells us is that this equation needs to get larger in order to reach Keq. So the reaction will proceed in the direction that helps us reach Keq. And if it needs to get larger in order to reach Keq, then that means that it's going to be creating more products, which means the reaction would proceed in the forward direction. So whenever Q is less than Keq, your reaction will proceed in the forward direction. The next scenario would be if Q is more than Keq. If Q is more than Keq, then that means that your fraction is too large. And to get a fraction to equal a smaller number, you need to increase the value of the denominator, which means we need to increase the amount of products, which indicates that our reaction is going to proceed in the reverse direction. So whenever Q is more than Keq, the reaction will go in the reverse direction. The last one is whenever Q is equal to Keq. That tells us that the forward and reverse reaction rates will be equal. So we will have equal rates. We'll talk way more about what direction a reaction will proceed in the next video when we go over Le Chatelier's principle.